the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
Good morning. Welcome to Deciphering C++ Coroutines. This is me. This is how you can reach me. And you might remember I was on this stage 2 years ago with a talk about coroutines. And this is now part 2 so a direct sequel to that other talk. This talk assumes familiarity with the contents that we covered in part 1. So you should know about the basic mechanisms of the language mechanism of the coroutines already. If you're watching this on YouTube right now and you didn't see part 1 and you don't know coroutines yet, I suggest that you pause and go search for Deciphering Coroutines CppCon 2022 and watch that talk first. We'll do a really quick recap of part 1 now, but it will be very brief, so hang on tight. So a coroutine, in the simplest terms, is just a function that can be paused in the middle. And then you can resume it later, and all of your surrounding function state will still be intact, just the way that you left it, and you will just resume at the same place where you left off earlier. There's 3 major components to the language mechanism that you need to keep in mind. The first one is the return type, which is just the return type of the coroutine function. This is a user-defined type that defines the interface through which the caller can interact with the coroutine. C++ allows for a wide range of behaviors here and many different kinds of interfaces. And one goal of this talk is to help us better understand what the design space for these types is. So as I said, the return type is just the return type of the function. So when we call a coroutine, we can really think of that as like calling a factory function that creates this type, which is then a handle to the coroutine state. Notice how we cannot tell by just looking at the signature whether this function is actually implemented as a coroutine. This is different from most modern coroutine implementations in other languages where you have to mark each coroutine by like an async keyword in the signature. Since C++23, we now have in the standard library one coroutine return type that ships with the standard library, that's a std generator. And that allows you to yield values from the middle of the function back to your caller. Std generator also implements the range concept, so anything that works with ranges can consume the values that are generated by this generator. If you don't really see how this is useful, I suggest as a little exercise, just try implementing an iterator that traverses a complex data structure like a tree or a graph. And you will see that it is surprisingly difficult, in particular if you compare it to the simple solution where you just loop over the elements. And in part 1, we actually showed everything that you need to implement a generator. So if you've seen part 1, then you should have a rough understanding for how the std generator works. The second part is the promise type. And while the return type determines the user-facing interface of the coroutine, the promise type is part of the compiler-facing interface here. It provides us means for customizing the behavior invoked during startup and shutdown of the coroutine. So in part 1, we assembled like this little cheat sheet here that shows us all of the customization points. I will not go through that in detail again for time's sake. And then the final part that we discovered is the awaitable, which is also part of the compiler-facing interface. And this allows us to specify what happens whenever a coroutine is suspended or resumed. You can think of the awaitable like every type that can be co-awaited on is an awaitable. So like co-await is the operator that puts a function into suspension, and the awaitable then customizes what happens there. Again, this is the overview that we saw in part 1. And then we also looked at how all of these different parts are connected and how we can traverse this little graph to like pass data in and out of a coroutine. If you want to use the cheat sheet to follow along the talk, you can use this QR code to look at it again. I will leave this up for a second. So why am I back now here with the part 2? So at the end of the last talk, I said, we now understand everything about coroutines, the language mechanism, but that just means we understand all of the boring parts. So we can now start doing the really interesting stuff that is exciting about coroutines. So this talk is about one of these interesting use cases and one that is of particular prominence, namely asynchronous computation. So other languages have dedicated language features for this. C# was probably the first one that popularized this. There's also Python, JavaScript, Rust. They all have this async await feature. And if you work with one of these languages, it's very likely that you've seen that before. But if you work with this in the other languages and you first encounter coroutines in C++, then you will notice that, like, from just understanding these basic language mechanisms, it's not really clear how you can do something like async await with C++. And the goal of this talk is actually to show you how that works to bridge that gap. I will not have much time to motivate why async await is useful to have in the first place. If you don't know it from other languages yet, I suggest a good exercise is just look at the documentation for Boost ASIO. Start by looking at the blocking echo client server example. And then it will have a bunch of examples for an asynchronous echo client server for the different language versions like C++, 11, 14, 17, 20. And just look at them in chronological order. And by the time you arrive at coroutines, you will hopefully understand why this is useful to have. If that sounds like too much work, there's also this great talk by Andre from Code Dive last year, which is an entire talk dedicated to motivating this use case. It got way too little attention so far, so please check it out if you're interested in this. A word of caution, I will at times lead you astray. This is intentional and will hopefully help to deepen your insight. I will not be covering multi-threading at all in this talk. That's an entirely different can of worms. And this is also not a best practice talk. All of the code that you will see here is very much slide where it's meant to illustrate a point. It's not supposed to give like a best practice. So let's start by building a mental model for what we're trying to do here. So we can think of coroutines, and an analog that is often given is coroutines are like cooperative threads. So what does that mean? So let's say we want to do some task, right? And it's a complex task, so it consists of several functions. We have an outer function that depends on a partial result that is computed by a middle function. The middle function, in turn, calls an inner function, which retrieves like some data through I/O, right? And the simplest way that we can do this is the inner function will just use some blocking I/O function, and of course, this could take some time. So the obvious problem here is that while the inner function is waiting, nobody else really can do any useful work here, right? The entire thread is occupied now just waiting for this asynchronous result to come back. So what if we, instead of just waiting here, we could just suspend all of these functions, put them somewhere on the side, and then do some useful work on the main thread in the meantime? Right? That is our main motivation. That is what we want to do here. So one straightforward solution to this is you just spawn a thread, right? So you could use async, or you could roll your own mechanism using JThread and futures. And then when you call spawn task, what that will do is it will just spawn up a new thread. And then while inner function is waiting, it's just blocking that one thread, but the main thread can do other useful stuff in the meantime. So of course, this is not perfect, right? Thread creation is a rather expensive operation. Also, thread switching is rather expensive, right? So if you have a lot of these pending operations hanging up in the air and you need to switch between different task contexts, that's not cheap. Also, the block thread that is sitting there on the side, like depending on how smart your scheduler is and how aware it is of what's going on with the I/O, it might still consume a lot of CPU cycles. Also, big problem with threading, of course, you now need to make sure that all access to shared data is synchronized correctly, which is a big can of worms. And there's probably many other problems. So this is not a solution that scales well, right? Like if you only have a small number of tasks, you can probably use this quite well. But if you need to handle like tens of thousands of connections, then this will probably overload your system in unreasonable ways. So an alternative to just using operating system threads is green threads, which are sometimes also called stackful coroutines. Sometimes you also hear the term fiber or user mode threads. And this is like one of the most popular mechanisms for cooperative multi-threading. So the way that this works is we spawn a green thread. So this is just a user lamp thread. This doesn't require support from the operating system. And then in the inner function, when we just set up our I/O operation in a non-blocking way, then we suspend execution, and then we will be woken up later once the result becomes available. And what happens here is that when the green thread is created on the side, it is first suspended, and then what will happen is that the main function that created this thread will sort of switch over execution to the green thread, and then the green thread can start executing up to the blocking operation. At this point, the control will again switch back to the main function. The spawn task function will then return. Main can do useful stuff in the meantime. And eventually, when the I/O result becomes available through some handle to the green thread, the control is again switched over, and now the function can continue computing the task. And the important factor here is that, like, even though we were switching like between these execution contexts, these are not operating system threads, right? So this all happens in userland. We're simply switching out the call stack here. So this has way less overhead than the operating system threads. We also don't necessarily require synchronization because everything can execute on a single thread. The green threads cooperatively decide when to suspend and resume, right? Like you cannot be preempted like you can be with operating system threads. Here, each thread voluntarily gives up the execution context. But the intuition about the control flow here is very similar to threads, right? Like if you understand how to solve the problem with threads, then the only thing that you need to decide here is like what are the points where you actually hand control over to the other context. But otherwise, it's a very similar way of thinking. C++20 coroutines are different because they are stackless, right? With C++ coroutines, I can suspend the function, but I can only suspend the function that I'm currently executing. If I have such a stack of nested functions and I want to suspend all of them, I can't really do that. Unless, of course, I suspend them all one by one, but like, how would that work? And that is really what we are going to focus on in this talk here now. Like, how can we make this work? If I can only ever suspend a single function at a time, like, what is a good pattern to suspend a larger execution context that is bigger than just my function? So if you're coming from such a thread-based intuition, then the first idea that you might have is something like this. So we start with a blocking I/O function. The first thing that we need to do is we need to turn this into a coroutine, right? Otherwise, we can't suspend anything here. So we turn the blocking operation into an asynchronous operation, and we make the asynchronous operation return something that we can co-await on. Since this is now a coroutine, that also means that my return type now becomes a coroutine return type. You will often see this in presentations or in libraries called task. There's also other names, like the standardization committee seems to like the name lazy now. I call it async here because this is essentially what the async keyword does in these other languages. The reason we don't just call it async in C++ is that in C++ there's a design space here, right? There's no single answer how this thing should behave. So like think of async here as like a placeholder for like whatever kind of task object you would want to use here. But once we have this, we're done, right? That's all of the changes that we need to make to the implementation. We will figure out like what this async object needs to look like in a bit. But let's go on for now. So with the middle function now, we have sort of the same situation again, right? So the inner function just resumed and we cannot continue. So we need to turn this into a coroutine as well. And now you might already notice something interesting here. Because when we expand the co-await call down there, we see that what we're awaiting on here is an async object. But what we're returning is also an async object. And if you're coming like with the intuition like from writing a generator, then this is very different, because now all of a sudden we have this async object fulfilling two roles at once. It's both acting as the return type for a function, but it is also acting as an awaitable. And this is true for all three of these functions now, right? So let's look at the interface that we would use for resuming such tasks now. So once everything has bubbled up, we will end up in main, right? And main is not a coroutine, so it will just get this async object, and that will just be the handle to the task here. So what will happen here if we look at the call stack, right? So we spawn all of the functions. Eventually, we will reach the inner function, and the functions will start suspending, right? So the inner function goes away, and then one by one, they all suspend, and we end up back in main. Now main can do other stuff, and eventually we reach this point where we want to resume computation. So we do the whole thing in reverse, right? Like we await resume on the outer task, and then we reconstruct the call stack, just like we had before, right? Like that's what we would be doing with green threads. So let's zoom in a little bit, like how this looks like in the outer function. So the outer function is here. It calls the middle function. It gets this async object back. Now we co-await on this, so the outer function goes to sleep. It's suspended now, and eventually main will wake it up. It starts running again. Await resume will get called. Control is handed back to the outer function. It continues executing. But wait a second. If it continues executing, that means it falls out of the co-await and it falls to the co-return. But that's not what we wanted, right? We wanted to continue executing the middle function and then continue executing the inner function and then process the IO result. So this does not work. You cannot resume nested coroutines from the outside in. Because once a coroutine has been resumed, it cannot be suspended again unless we call co-await again, right? You only get one suspension per co-await call. But we do not know from the outside how often we need to suspend before the inner function has completed its execution. So what we really want co-awaiting a function to mean is wake me up only once the once the task that I'm co-awaiting on has completed and all of its results are available, and you can give me back like the final return value from that. Okay, let's take a step back here. Like, what is a call stack anyway? So if we look at our stack frame in memory, right, we have this base pointer that gives us the bottom of our call stack, and then we have the stack pointer that we move along as we push and pop elements from the stack. And in between those two lives like all of the state that makes up the local state of our function. And then below that, we have the frame pointer and the instruction pointer of our caller, right? So that we know which address to jump back to when we finished executing this function. And then in memory, we have this linked list that is formed by the different stack frames, right? So we have the base pointer register, which is sometimes also called the frame pointer. And then if we just follow this frame pointer through this list, then we get through all of the nested stack frames. So really, this is just a singly linked list of stack frames with links from callee frame to caller frame in memory, right? And if you look at like when your debugger, for example, displays your call stack, that's exactly where it gets this information from, right? It just traverses this list. So what we need to do is we need to find a way how we can connect a coroutine to its caller, right? So let me introduce some more colors here to make this a little bit easier to see what's going on. So from now on, whenever you see the indigo color here, that will refer to the inner function in this context. Whenever you see orange, that will refer to the outer function. So just think indigo, inner function, orange, outer function. So in this case, again, like the same async object here fulfills two roles. For the inner function, the async object fulfills the role of the return type, but for the outer function, it fulfills the role of the awaitable. If we look back here at our cheat sheet, so the inner coroutine builds the async object and hands it back to the caller. The caller then awaits that async object to get notified when that inner coroutine is finished. So in this diagram that we built in the first part, the caller and the coroutine were separate. But in case of the async object, for the same object, the caller and the coroutine are the same. And the inner coroutine, the one that is actually suspended, does not have access to the async object that it's returned as its return type anymore. It can only reach it via the promise by like awaiting on a different awaitable. So yeah, this is a bit confusing. So let's try to sort this out. So let's first try to look at the two roles separately. So in the role of the return object, what is going on here? So we keep a coroutine handle to ourselves, right? That is just what we also saw in the first part of the talk. When the return object is created, we hand the handle to the constructor of the promise, and then we save it. And this is now the handle to the inner function, right? So the inner function creates this async object that it hands back to the outer function, and it saves in there a handle to the inner function. And this is really all there is to the return object, right? This is exactly the same as what we've seen before. But now what happens in the other role? What happens in the role of the awaitable? So to make it make the async object an awaitable, we have to implement these three functions. So await ready is, in our case, always false. We're not looking at await resume yet, but now when we get to the await suspend, we notice something interesting. Because there is again a handle here that's passed as a parameter. But this is the handle to the outer function, right? When you call co-await on something, then the await suspend function passed to the awaitable is the handle to the function that is co-awaiting. And that is the outer function here, right? So we have these two handles, and they're pointing to the two different levels of the call stack. So let's just store this handle also. And now what I have is, on the one hand, the return object has a handle to the function that is computing the async task that this object is referring to. But then in the promise, I have a handle to the caller that is awaiting the result that this function is supposed to compute. And now if I look at what happens when I nest these computations, then I get a data structure that is very similar to what we had with the call stack before, right? I again have a linked list, in this case of like coroutine handles to promises. And they again point from callee to caller. So I built this structure now that is equivalent to the call stack, so I should be able to now resume the caller from a nested coroutine. So, as we've seen, like the handle to the caller is stored as a data member in the promise. And now what I want to do is in the final suspend, so when this async task has finished all of its work, I want to hand control over to that caller. So the only thing that I can do in the final suspend is return an awaitable. And I want that awaitable to somehow resume my caller now. So how can that look like? Well, await ready will always return false, right? Because I don't want to continue executing this inner async task, right? It has done all of its work. I want it to go into suspension, and I want it to go into suspension indefinitely, right? So await resume will never be called. I don't need to do anything about there. So in the await suspend, what I do, and this is the only interesting part, is here I hand back the handle to my caller that I saved in the promise before. And what happens here is a symmetric transfer, right? So this was something that we covered in part 1 at the very end. Await suspend in many cases just doesn't return anything. But if await suspend returns a handle to another suspended coroutine, then that means we transfer control over to that coroutine. So let's look at this in a little bit more detail. So what we have here is we're currently in the inner function. Like somebody resumed the inner function. We don't really know what that is. I just called it base here. Doesn't matter. We will never get to that. And our goal is now to get from the inner function to that teal arrow up there in the middle function that called it, right? So the inner function got woken up. It managed to do all the work that it's supposed to do, and now it's done, right? So the first thing that it will do is, as part of the co-return call, the return value function in the promise type will get called. I will store the result somewhere in the promise so that it can be retrieved later. And then that function is done, right? It reached the end of the function body, and now final suspend is called. Now in final suspend, what we do is we return this special resume caller, awaitable that we built earlier. And at this point, we use the symmetric transfer to return this handle to the caller that we have stored in the promise all along. And now what happens, look at the call stack, right? So we have the inner function on the call stack now. And now because of the symmetric transfer, we swap out the inner function with the middle function, right? So that is the crucial part about the symmetric transfer here, that the two functions just switch their places on the call stack. So the inner function is suspended now, and the control has been handed over to the middle function. So we're now up there where we want it to be. And now, as part of that function being resumed, await resume is called on that awaitable. This will retrieve the return value that we stored in the promise earlier, and then that value will fall out of the co-await expression. Notice that the inner function is at this point suspended, but it's still alive. And that is vital because the return value that falls out of the co-await expression here is stored in that promise. So we cannot destroy it yet until it has actually been saved in that local variable in the outer function here. So only after await resume has returned and we actually drop to the next line, now the async object corresponding to the inner function, which was just a temporary on that line where we called the co-await, now that temporary will get dropped, and its destructor will actually clean up the state of the coroutine. And now it's safe to do that because we don't need the promise anymore, right? The return value has been moved to that local variable R up there. So this is, again, on one slide, the overview of what happens here, right? So we, through the await suspend, we are able to fill this orange handle up there in the promise, and then that's where we keep the handle to the caller. And then eventually, when the inner function has done all of its work, it reaches the final suspend. That is when we use the symmetric transfer to hand the control over to the caller. So this gives us a large part of the puzzle, right? This explains how we can walk the call stack back up, how we can get from one function to the next. But there's still one thing that we haven't figured out, and that is who resumes the innermost coroutine, the one that is blocked waiting for that I/O operation, right? Somebody needs to wake that up, and it has no callee that can wake it up. So how does that happen? So if we look at the co-await call here, right? If we pull this apart, then the awaitable that is returned here, that's not an async, right? That's a different kind of awaitable. This is something that is provided by my I/O library, and it plays by different rules. So in particular, what's really happening here is I'm setting up an asynchronous I/O operation. And before I go into suspension, I somehow have to tell something in the I/O machinery that, hey, I'm waiting for this asynchronous I/O request to complete. Please wake me up once that happens. So what I need really here is I need to have some kind of scheduler, something that I can tell that I'm waiting for this asynchronous I/O result to complete. And that scheduler then will have to wake me up once that happens. So we need this magical scheduler, right? And where does this come from, right? Obviously my asynchronous library will provide me something like this, but how can I get it to this point? How does the inner function have access to this? Because the scheduler is typically something that the inner function does not decide about, right? This is something that is decided much higher up in the call stack, typically even in main, right? This is where the scheduler gets created. This is where this decision is made. And then somehow I need to propagate this information all the way down into my inner function. So the obvious way to do this is to just pass it along, right, as a function argument. But this is really annoying, right? That means now that all of the functions, even the ones that don't do any I/O themselves, need to pass along this scheduler object. And yeah, it bloats up your function signatures. There must be another way. So our async awaitable, it has a link to the caller, right? But when we establish that chain, we can pass along the scheduler in the same way, right? At the point when I'm in the await suspend where I establish that link, instead of like just saving the handle, I can also pull out other information that my caller already has and propagate that down. So in this case, if my caller already knows about the scheduler, then at this point I can just pull it out and save that information in my own promise, right? So now we're propagating information sort of the other way down the call stack. There's one slight complication here, and that's this promise type. Because this promise type is not the same as the promise type further up. If you think about it, like we have all of these functions and they all have different return types, right? And the async object is templated on the return type. So if the caller and the inner function have different return types, that means they have different async objects. And since the promise is a nested type in the async objects, they will also have different promise types. So I need to use a template here, right? There's two different promise types here. Like this is the other guy's promise, right? So it's a different type. But this is a bit too general, right? Because this cannot just be any promise. This has to be a promise that has this field that stores the scheduler, right? Because otherwise it doesn't work. So really this is a special kind of promise. There's certain rules that it has to follow. And this is now an interesting thing that happens in asynchronous computation, because we now have a design space here, right? Like we cannot fully erase the type. The promises have to be somewhat uniform in some way, right? And like this is something that you would probably want to have standardized to some extent, right? Because if you're now thinking you're combining different asynchronous libraries and they all define their own promise types, then doing things like this become really difficult. Because if you have like different promises, different kinds of promises on the asynchronous call stack, then like you can only propagate so far before you hit something that doesn't play well with your mechanism. So how do we ensure that the scheduler is actually there when the inner function hits this first call where it awaits the I/O operation, right? Because if everything just starts running, then the scheduler has no chance to propagate. The scheduler can only propagate the first time the inner function suspends and gives control back to the caller, right? Because that's the point where we establish the links. So really we want to spawn up all of these tasks lazily. We want to suspend always on the initial suspend so that we have a chance to build up this data structure and propagate all of this information through. So if we now look at what happens if we have lazy async objects like this, is okay, like the we call the middle function, we co-await it, right? When the middle function starts up, it immediately goes into suspension because of the initial suspend up there. And then it's just paused. But wait a second. That means we just paused and we stopped everything before we ever reached the call to the inner function, right? So we're now not waiting for the I/O operation. Nothing has been set up. We just suspended right away without executing anything. So that's not good, right? Like what we want to do is, yeah, we need to suspend because otherwise we can't establish our list, but we still want the function to do its thing. So fortunately, symmetric transfer can once again help us here. If we look again at like the different kinds of handles that we have here, we get as an argument the handle to the outer function. But remember that in the very beginning, when we set up the async object, we already saved the handle to the inner function. So we can now use symmetric transfer to, like, once the await suspend has finished, to immediately hand control back to the inner function. So let's look at that in a little bit more detail because it can be a bit confusing. So we're down at the bottom, right? The outer function is spawning up the inner function, which in this case is called middle function. That function starts up, and as part of its ramp up, initial suspend is called, and initial suspend just says right away, put me back to sleep. So control goes back to the outer function. Now, as the outer function wakes up, it calls await suspend on the awaitable that it awaited on, which is the one that was handed to it by the middle function. And now the middle function, through this symmetric transfer trick that we saw earlier, just resumes itself, right? So now the outer function is suspended, and the middle function takes its place on the call stack. And that's how we get to have our cake and eat it too in this place, right? Like we need to suspend on the first the first opportunity before the function starts executing, because we want to make sure that all of the data that the coroutine body depends on has been propagated. But we also want the function to actually start doing useful stuff once that propagation has happened. So we need to do this little dance here to make that happen. So passing a scheduler along here, like we know how to put data into a coroutine from the outside, right? That's one of the things that we covered in part 1. So we can put the scheduler from the outside into the promise. And we can use the await suspend function to then propagate it along. But like, why should we stop at the scheduler here, actually? So how about this? I define a base class for all of my promises. And this base class acts like a node, and it points to the promise of the caller and another pointer to the promise of the child. And now in the await suspend, I just say, okay, like if the promise is like one of these promises that derives from this base class, I establish the links, right? I establish a doubly linked list where I always know what is the promise base of my caller and what is the promise base of my child. And now I can put anything I want into the promise base. Any additional data that I want to propagate, I can just put it there. Because what happened now is that the asynchronous call stack is just another data structure. And just like a data structure, I can iterate this, I can manipulate it, I can read data, I can put data in there. So one little demo that I did here, and you can find the source code for this at the Godbold, is like debugging coroutines is really annoying, right? Because of the way that we set this up, and because of the symmetric transfer that we do to actually get the coroutines running, right? Like in the beginning, we saw that before in the example, right? Like when the outer coroutine hands control over to the middle function that it was calling, what happens is a symmetric transfer, right? So the outer function disappears from the call stack, and the middle function takes its place. So if I put a breakpoint into my innermost function and I look at the call stack window, all I see is the inner function, because all of its callers have disappeared, right? They symmetrically transferred over to the inner functions, and then they are no longer on the stack. So how can I get now the context back, right? That's one of the big problems with asynchronous programming. And we had a talk earlier this week, like how you can get that information back, which I'll have in the references at the end. But like one thing that I can do is, hey, my call stack is just a data structure. So I can use a data visualizer to get it back. Like this is the data watch window in Visual Studio. And like once you have this information in the promise, this is about like 15 lines of NetVis code in Visual Studio to get a visualization like this. So it's not great, right? But like for 15 lines, that is not bad. And then if you combine this with the STD source location feature from C++20, you can actually have a surprising amount of debug info in these things and get a lot of information about the context. So when our call stack is just a data structure, like think about what that means, what you can do now. You can resume any function that you want in the call stack. It doesn't have to be the innermost or the outermost, right? If you want to have like an exception, like error handling mechanism that just resumes anywhere further up the call stack, you can do that. You can splice two call stacks together if you have a use case for that. You can expose the range interface and then use range algorithms over your stack frames. But this is still, in the end, this is, even though we made the switch from singly linked to doubly linked, this is still just this linear structure of nested tasks. So let's see what happens if we make one more tiny change. Now it's a tree. Now it's a directed graph. So coroutines are extremely powerful for manipulating the control flow between functions, and actually way more powerful than async await in other languages is. To achieve best results, there should be some amount of uniformity between the coroutine types here, right? Like we saw this when we tried to put information into the promises. Like ideally, there should be a uniform mechanism that all of the libraries can agree on, like what the protocol is here. And like they don't have to support all of the features, but at least like I should be able to figure out like, hey, which features do you support and what is the interface to this? The C++26 senders receivers take a first step into this direction, but the work is far from complete. And I think the reason that we haven't figured this out yet, that is one of the reasons why we don't have more types like this async type or like a task type in the standard library yet. But that's also an opportunity now for us, right? Like this has not been set in stone. And like my feeling is that the amount of experience that we have with this feature and with these patterns in the community is still fairly limited, right? There's not that many people looking at it. So my hope is that we can get more people to like just try interesting things here and see like what are the useful patterns that we can use here, and join the conversation, right? Like just play around with this, see what cool things you can come up with, and then if you manage to find something that nobody else has before, like talk about it, right? Maybe bring it to the Beeman project, I don't know. But just like look at this, we really desperately need more people looking at this. So here's some references for other talks. Shout out here to Louis Baker and Mateusz Pusch, who helped me a lot in preparing these talks. Of course, all remaining mistakes are my own. Dietmar gave a great talk earlier this week about creating an HTTP server with a sender-receiver. If you want to see how you can actually properly do debugging, check out the talk by Ian Peterson and Jessica Wong. Dimitri yesterday gave a talk about like what a framework could look like that uses coroutines and also has algorithms for combining tasks. And Michael will be talking this afternoon also about senders to wrangle concurrency. I don't know how much coroutines will be in there, but I'm sure it will be great. And that's all I have. Thank you.
Thank you for the talk.
Thank you.
Is it possible to capture a lambda in the return type? So I'll have something to be called every time internally in the coroutine.
Sure, why not? I mean, the return type is just like any other data type that you define. If you want to capture like some function that you invoke, yeah, no problem.
Thank you.
Yeah.
Could you please clarify a little kind of the domain? You were saying that the schedule has to be passed from the top.
Yeah.
And kind of that's what a bit confused me, because I would think that only the inner function actually knows like what async IO it does. And if it's interfaces with the library,
yeah.
It makes sense that the library would also tell you what the scheduler is. So
right.
It might be global, it might, however library internally captures it,
yeah.
But you should be able to ask. So why do we have that information, that piece of information coming from above, where there's no other information about how exactly we do async IO? Everything is local to the inner function, except that one bit.
Yeah. So the thing is, like, if you think about the schedule, like a concrete example here would be the IO context in Boostagio, right? So this scheduler, it maintains a bunch of state that is not local to the inner function, right? It has to keep an overview of like all the outstanding IO requests that are happening in the system. It needs to provide like an entry point, like how you can sort of like pump the message queue whenever one of these becomes available. And this is all state that is not local to the inner function, right? So you wouldn't want to create this scheduler object locally in the inner function and then pass it to the async call.
Yeah, but wouldn't the library be able to return me like an instance of that global entity if I just...
Yes, of course. Yeah, that's then a question, right? You might not want to make it a global variable, right? You might still want to have, because you might want to be able to have different schedulers around, for example, right? So it's, there has to be some entry point how you can get this, right? And like this, what I showed is just like a very convenient way to do this, right? It's certainly not the only way, right? Like depending on what your framework looks like, there might be other ways that might actually be easier in some cases. David.
So coroutines has been standardized for several years now.
Yeah.
And it appears that figuring out how to use this in a practical way seems to be an ongoing area of research. Do you think that we standardized this too early?
I mean, we haven't standardized much yet besides the actual core mechanism, right? So I think like all of these things that I've shown there, the standardization is still in flux. But I do feel that we are now at a point where it's worth having additional eyes on this to make sure that, like, once we do put a task object into the standard library, and there are proposals floating around for this, that we don't close any doors that we might regret later.
So going back to his comment, it could also be a thread local, right? I mean,
yeah, of course, yeah.
A scheduler.
Right.
That's one way to short circuit this complexity.
Yeah, that's true. Yeah.
One question I had was, you had this resume called all the way from the main again. Typically, the I/O is completed somewhere else.
Right.
So there is some event or something that triggers.
Yeah.
And that's where the resume can be called.
Yes.
Inner resume can be called from that side.
Yes. Yes.
In which case, this complexity of I will replace myself with my parent.
So
that may still be there, but the forward, the down call replacement can be avoided.
Yeah. So there's several factors that play together here, right? So there is this entity which I call the scheduler, which is responsible for waking up the innermost coroutine, right? And all that scheduler needs to know is really what is the handle to the coroutine that is waiting for this particular operation. It does not need to know about, like, the whole stack that comes with that, right? So we do localize the information here, right? The scheduler just knows about the innermost, and then each coroutine along the stack knows about its caller, right? The question is still, like, how, like, the innermost coroutine somehow needs to get access to the scheduler where it can register itself with, right?
Right.
And this.
Let's say we pass through thread local.
Right.
Avoid
yeah.
that.
If that's good enough for you, then you can just put it in a thread local. But, like, other people might have constraints that don't make that a good solution.
Okay.
Yeah.
Okay. Thank you.
Of course. Yeah. Please.
Well, first, thank you very much. It's very fascinating stuff. I just have one question, maybe a naive one, as somebody who's not very used to doing asynchronous AO.
Yeah.
So I understand that coroutines are way more flexible, right, than green threads, for example.
Yeah.
Oh, they seem to be.
Yeah.
But considering the little dance that we're doing, we're rebuilding a whole data structure and stuff like that. Right now, today, is there any practical examples where coroutines are more interesting to use for async I/O than green threads, for example?
Yeah, that's an interesting question. So it's like I would say, like, for asynchronous I/O, like if we're just talking about the user experience, then like green threads actually have advantages, right? So, like, one problem that I did not talk about is there's this problem of function coloring. Bob Nystrom wrote a blog post about this. I think that was in the context of Python. The problem that you have is, if you're building such a stack now of computation, is every single function on this stack needs to be an async function, right? So it's like this async keyword, or like these task types, they're viral, right? You have to put them on everything. And if something is in between that doesn't play nice with them, then it doesn't work anymore. And green threads don't have that problem, right? With green threads, it's just, I suspend the whole thing, hey, and it's fine. So that's, that's an advantage of green threads. With the performance, I don't feel qualified to speak too much about performance. I know that, like, green threads are not doing too bad there. I don't know if like this stackless approach is definitely a win there. So the only thing that I can say is that, like, all of these other languages, right, they have settled on using stackless coroutines. So it is a paradigm that has been very successful, in particular, like, in the last decade in this area. And the stackful coroutines, the green threads, have sort of fallen out of fashion since. I don't know how good the reasons are for that. Like, maybe, yeah.
Okay, thank you. Guess we'll see.
Okay, yeah, thank you very much. Okay, then we're out of questions. Thank you very much.